So here we're given two sequences of amino acids, one normal and one mutant. And under each amino acid is a list of the possible sequences that could cause that amino acid. Using these, we need to determine the genetic sequences of both. So we know that methionine and tryptophan only have one possibility, so there's no choice there. Then we see that there's a difference in the third amino acid. If you look closely though, you can see that if you were to add an A in front of the U, then that would change it to AUU, and the phenylalanine to isoleucine. And the next, CAC, would change the threonine to histidine. Finally, the last few have to be UAA, because the mutant sequence needs a stop codon. So that shows you that the first part of the normal genetic sequence has to be AUG, UGG, UUC, ACU, AA. And then it can be a few options such as AAA, GGU, or AAG, GGC. So now I'm going to talk a little bit about how the addition of that A resulted in the production of a truncated nonfunctional mutant protein. So here's the genetic sequence that we have. AUG, UGG, UUC, ACU, AAA, GGU, and I've added a stop codon here at the end, UGA. And then these are the corresponding amino acids. So let's look at what would happen if we were to add an A into the sequence right here. So if we were to do that, then the whole sequence would shift down one base pair. So instead of this original sequence, I'm going to write our new sequence down here at the bottom. So we'd have 5' AUG, UGG, AUU, CAC, UAA, AGG, UUG, and then A at the end. So it starts off looking pretty similar. We have both methionine and tryptophan in both, but then it starts to change once you go to where we've added the A. So instead of having phenylalanine here, we have isoleucine in the new sequence. Then instead of threonine, we have histidine. And instead of continuing on to lysine and glycine, we have a stop codon, UAA. So this is what creates the truncated nonfunctional mutant protein. The new stop codon stops transcription and the sequence becomes shorter.